Hi, today I'm going to talk about the solutions for Atcoder Beginner Contest 388 problems A to E and G. And for problem A, we have a string and we need to output the string with the first character and UPC. So for this problem, we just need to directly get the first character of the string and combine it with UPC. And let's look at the code. And so we just need to input the string and afterwards get the first character of the string and add UPC behind it and output the answer. Problem B is also straightforward since the problem states that there are n snakes and each one has a thickness of T and length of L. And the weight of a snake is the product of its thickness and length. And we need to find for K from 1 to D the weight of the heaviest snake when every snake's length has increased by K. So since N and D are all really small, they're only less than 100, we can just directly simulate the problem. And let's look at the code for further details. So we input the T and L for each snake, and afterwards we just directly loop from 1 to D, and for each increase we keep track of the answer, which will be the maximum weight of the snake after their length has increased by I. So we can just loop through all these snakes and for each one calculate the maximum weight when its length is increased by I. And afterwards we output the answer that we get for each value of I. For problem C, we have n mochi arranged in ascending order of sizes, and if we want to stack two mochi on top of each other, then the top mochi has to have a value of A that is at most half of B. And we need to find how many different kinds of mochi that can be made. And a different kind of mochi is when at least one of the mochis is different. And so for this problem, since the values of A are already sorted, we can just loop through all the values from the end to the back, and for each value, like for example 10, we can count how many Kagami mochis can be formed when 10 is at the bottom. So this means that when 10 is at the bottom, it can form a 2 mochi stack with 2, 3, 4, 4. So these 4 mochis can form a stack with the mochi with value 10. And if we look at the mochi with value 7, it can form a stack with 2 and 3. And so we can just loop through from the end back to the front and count how many Kagami mochis can be formed when the current mochi is at the bottom of the stack. And we can add the number of mochis that can be put on top by a lower bound function or just using 2 pointers. And let's look at the code for the actual implementation. So I used 2 pointers to solve this problem, and I first just inputted all the values, and this sort is unnecessary because I didn't see the problem that the values of A are already sorted. So afterwards, we first start. This loop is just looping through the possible mochis that can be at the bottom of the stack. So J keeps track of the first J mochis that can be put on top of the current mochi I. So for this part, for each mochi, we first decrease the value of J until we can put all of the first J mochis on top of the current mochi. So if AJ is greater than AI divided by 2, then this means that it can't be stacked on top of AI. So we need to decrease J. And afterwards, if J is still greater than or equal to 1, then equal to 0, then this means that the first J mochis can be stacked on top of the current mochi. So we can add this count to the answer. And in the end, we just output the answer. And next, for problem D, we have N aliens on the planet, and each become an adult I years later, and each of the aliens have AI stones. And when someone becomes an adult, every adult who has at least 1 stone has to give 1 stone to the alien who has just become an adult. So we need to find how many stones each alien will have after N years. Let's first look at a sample input to understand the problem. So for this sample 2, the first alien will give a stone to the second alien when it comes to age. And afterwards, the second alien will have 7 stones. And when the third alien comes to age, both the first and the second alien will both give stones to the third alien. And so after this, the first alien will only have 2 stones, while the second alien will still have 6, and the third alien will have 9 stones. And this goes on until the 5th alien has also come to age. And so one key thing that we notice is that since the first alien has enough stones to give to all 4 aliens that come after it, when each of the aliens come to age, it will give stones to all of them. So the first alien will give stones to all of the aliens that come after it, and the second alien will also give stones to all 3 aliens that come after it. However, if we notice that if the first alien only has 3 stones, then it will only be able to give stones to the 3 aliens that come after it. So we notice that there's a range that the aliens can give stones to. So since we don't want to add the values for each of the aliens one by one, we can use a prefix sum. And the range that each alien will be able to give stones to is the minimum number of stones that they have, and the minimum number of aliens that come after them. So for example, if the first alien only has a of three stones, then they can only give to a minimum of 3 people or the 4 people that go after them. So we find the minimum of these two numbers, which is 3. And since we don't want to add values to this range one by one, we will need to keep track of a prefix sum. So in this case, for the first alien, we can keep track of a sum array and add 1 to the alien that goes after it, and subtract 1 to the end of the array, since the alien will be able to give to all 4 of these other aliens. So we can, as we do this, we can keep track of another variable called count that can just keep track of the current value of stones that the alien will have gained. So for example, count add is initially 0 when we are at the first alien. So this is because the first alien will get no other stones. And when we move to the second alien, we can add count add by the current sum. So in this case, when we move to the second alien, count add will be 1, because we have just added the new sum from, which is the stone given from the first alien. And if we have count add, then we can now get the current number of stones for the second alien. So the current number of stones for the second alien is just the value of count add plus a 1 for the second alien. And we can further calculate, since we now have the value for the second alien, we can then calculate how many aliens the second alien can give stones to. And afterwards, we can further add to the sum array by adding 1 to the third alien and subtracting 1 to the last alien. And we can repeat this process each time, updating count add by the value of the sum and calculating the final value of stones that each alien has after they have given away their stones. And let's look at the code for more details. So we first input the values for AI, and then my add array is just to keep track of the current sum of values that we added for each alien. So we first loop from 0 to n, and for each value, we add cur add by the current value of stones that they have gained, which is stored in add I. So afterwards, we can increment AI by cur add because they have gained this cur add number of stones. And this part is just updating the prefix sum array. So we add 1 to the alien I plus 1, and we subtract 1 to the end of the range that the current alien can give to. So this is just the minimum number of AI and the number of aliens left plus 1. So we subtract 1 to this, and afterwards BI will just be the current number of AI minus the number of stones that they have given away. So this will just store the number of stones that each alien will have after n rounds. So afterwards, we can just print out all of the solutions. And one thing that we need to be aware of is that we need to use long for the answer. For problem E, we still have the problem of stacking mochis on top of each other. So the problem background is still the same, and this time we need to find the maximum number of stacks that we can form. And so this time the problem is different in a way that the stacks need to be formed simultaneously, so which is different from the previous problem. So let's first look at a sample for this problem. So for the first sample input, we can form 3 stacks by matching the mochis like this. And so we notice that since this problem is asking for the maximum number of pairs of mochi stacks that can be formed, we can use binary search on the maximum number of pairs. And when we do binary search, we can check whether a certain k is possible by matching the values of the beginning with the end. So since the A values are given in ascending order, we can the first k values will be the smallest, and the last k values will be the largest, and we can match the stacks like this. So the smallest one will go with the kth largest one, and they will match like this. So for each k, we can just define a check function to check if the first k can be matched with the last k. And by doing so, we can quickly find the maximum value of k. And so I first during the contest, I actually wanted to do a greedy method of just matching the greatest value that can be matched. So for example, I wanted to match 4 with 2 and 4 with 2. So anything that is just below the value of a divided by 2. But however, I noticed that this method failed on this case, like this kind of cases, since it would only match 2 pairs, since it would leave out the ones. And so this is why we need to use binary search instead of just using a greedy method. Since for binary search, if we're looking at the value of 3, then if k is equal to 3, then they can form pairs like this. So let's look at the code for the implementation. And so this part is just doing a binary search on the value of k. And so this part is checking if the first k values can be matched with the last k mochis. So if not, we just return false. And if this is possible, we will add 1 to the first value. And if this is not possible, then we will set the last value to m. And by doing so, we can find the first k that is not possible. And at the answer, we can just check if first is possible, and otherwise we can just subtract 1 to the value. And so essentially we just do a binary search, and for each one we just check if the value of k is possible. Next, let's look at problem G. And so problem G still has the same background, but now we have q pairs of numbers, and we need to only match the mochis in the range L to R. So this time, since we have q pairs and the range L to R, we can't just directly do the same thing as the previous problem. So let's look at what we need to do differently. So if we just calculate all the values again for each pair, each range, then this will exceed the time limit. So we need to try to improve this method. So we can keep track of another array B, which can store the first index that has a value greater than or equal to 2 times AI. So BI is equal to the first index that has a value of greater than or equal to 2 times AI. And so to give an example, we can look at the first sample input. So for the first sample input, the values are 1, 1, 2, 3, 4, 4, 7, 10, 11, 12, 13. And so BI for the first value will be 2, since this is the first index that has a value of greater than or equal to 2 times AI. And for the second value, this will also be 2. And for the third value, this will be 4, since this is the first value that has a value of greater than equal to 2 times 2. And so we can find b for the other values as in the same way as how we did for the first 3. And so we notice that for each pair, if the value of k is valid, we need BL to be less than or equal to r minus k plus 1. And this is because we're doing the same thing as previously, where in a range L to R, we match the first k values to the last k values, like this. So the first one will match to the smallest one, and the second one will match to the second smallest one in the k values. And so if we look at I when I is in the range L to L plus k minus 1, we need bi to be smaller than or equal to r minus k plus I minus L plus 1. And this is just applying what we got from these equations. So since we don't want to have to calculate this individually for each I, we can move I to the left side. So bi minus I needs to be less than or equal to r minus k minus L plus 1. And so we realize that we can just calculate bi minus I initially, so we don't need to calculate it again for each range. And so for each value of k, we can still do binary search on k in each of the pairs of integers. So in each range, we still do binary search on k, and we can find the maximum value of bi minus I that is in our current range of L to L plus k minus 1 using a sparse table. So if we use a sparse table, we can quickly find the maximum value in this range. And after we found the maximum value, we can just check if the maximum value is smaller than r minus k minus L plus 1 to see if this value of k works. And let's look at the code. And so this part, I just inputted all the values for A, and afterwards, this part I use a 2-pointer method to find bi for each value of I. And st is just the sparse table that I have, which represents the, and stij represents the maximum value in the range I to I plus 2 to the power of j. And this is just for the sparse table, and to find the maximum value, but you can also find the maximum value with other methods without using the sparse table. So the key is to just find the maximum value of bi minus I in the range L to L plus k minus 1. So there's no need to use these sparse tables since there are also other methods. So in this part, I'm just inputting all the ranges that we need to calculate, and for each range we do binary search on the value of k, and for each k we find the maximum value. This C is just the maximum value of bi minus I in the range L to k plus L minus 1. And if the maximum value is smaller than r minus k minus L plus 1, then this means that this k works, and we can just check the binary search like this. And so afterwards, this is just the same as the previous problem, and we can just, after we finish the binary search, we can just output the value that we get. And yeah, so the key is to just simplify the problem by using the maximum value of bi minus I. So in this case, we won't have to recalculate whether each k works again for each different range.